This lecture is part of a series of lectures on rings and modules that will be about symmetric functions. So we recall what these are. Suppose you've got the symmetric group Sn, and it can act on n variables. Let's call them alpha 1 up to alpha n by permuting them in the obvious way. And we want to know what are the invariant polynomials in alpha 1 up to alpha n. What this means is we want a polynomial in alpha 1 up to alpha n that doesn't change if you permute the variables. And there are some obvious examples. We could just take the sum of all the alpha i's, or we could take the sum of all pairs, so alpha 1 alpha 2 plus alpha 1 alpha 3 and so on, which is sum over I less than j of alpha I alpha j. I'm going to call this one E1 and this one E2. And you can go on like this. You can take E3 as alpha 1 alpha 2 alpha 3 plus all permutations of that. And you go all the way up to En, which is just alpha 1 alpha 2 alpha n. So these are called the elementary symmetric functions. But there are lots of other symmetric functions. For example, we can write down alpha 1 squared plus alpha 2 squared and so on, which you can see is equal to E1 squared minus 2E2. And any other symmetric function you can think of, at least that's a polynomial, if you do a bit of trial and error, you find it can be expressed as a polynomial in these. And this is what we want to prove in general, that any symmetric polynomial in alpha i's, meaning one that's invariant under Sn, is a polynomial in E1 up to En. So we've sort of found all the symmetric functions, at least the polynomial ones. And the key idea of the proof is to order the monomials. So we've got monomials alpha 1 to the n1, alpha 2 to the n2 and so on. And we want to put some sort of order on them. And you can ask what order? Well, there are many different orders. So there's a theory of Grosvenor bases, which is widely used in computer calculations with polynomials. And people working on Grosvenor bases spend a fair amount of time inventing different orders on the monomials in order to make algorithms more efficient. Anyway, we're going to use the simplest one. We're just going to use the lexicographic order. Where we say alpha 1 to the n1, alpha 2 to the n2 and so on is going to be greater than alpha 1 to the m1, alpha 2 to the m2 and so on if n1 is greater than m1 or n1 equals m1, n2 is greater than n2 and so on. So n1 equals m1, n2 equals m2, so it should be an m, n3 is greater than m3 and so on. So this is something to do with the order you would put them in if you were making a dictionary, an extremely boring dictionary whose entries were monomials and you're sort of entering them in dictionary order. So the algorithm works as follows. So we're now going to write down an algorithm to write f as a polynomial and symmetric in the elementary symmetric function. So suppose f is a symmetric polynomial. And the algorithm is we just kill off the largest monomial in f. And we're going to keep on doing this, and if you keep on killing off the largest monomial and replacing it by smaller monomials, you will eventually get down to 0. So how do we kill off the largest monomial? Well, we want to subtract some monomial in E1, E2 and so on. So we're continually subtracting monomials in the elementary symmetric functions, and that will eventually reduce f to 0. So this will prove the theorem. So suppose the largest monomial is, say, alpha 1 to the n1, alpha 2 to the n2, alpha 3 to the n3, and so on. Then we then we subtract alpha 1 plus alpha 2 and so on to the n1 minus n2 times alpha 1, alpha 2 plus all the rest to the n2 minus n3 times alpha 1, alpha 2, alpha 3 and so on to the n3 minus n4 and so on. And you can easily check this kills off the largest monomial and replaces it by smaller ones. So if we keep doing that, we eventually get down to 0. So this almost proves the theorem that any symmetric polynomial is a polynomial in these. Well, there's a slight problem. Where did we use the fact that f is symmetric? See, if you weren't looking very carefully at that proof, we didn't actually seem to be using the fact that f is symmetric anywhere, and what we seem to have shown is that any polynomial whatsoever can be written as a polynomial in the symmetric functions, which is obvious nonsense. Well, the key point is that we need these numbers here to be greater than or equal to 0. And the reason these are greater than or equal to 0 is you can check that if we've got a if f is symmetric and the largest monomial is this, we have n1 greater than or equal to n2 is greater than or equal to n3 and so on, as f is symmetric, which is quite easy to check. I won't actually bother giving that because it's a one-line exercise. So this has shown that every symmetric polynomial is a polynomial in the elementary symmetric functions. And there's one slight problem with this. If you actually take an explicit symmetric polynomial and try and write it as a polynomial in symmetric functions, you tend to get rather a horrible mess, and it's really painful to do these calculations by hand. One particularly important example are the polynomials Pm, which are given by alpha 1 to the m plus alpha 2 to the m plus alpha 3 to the m and so on. And the problem is, how do we write these as a polynomial in the symmetric functions? Well, the first few aren't very difficult to do. So P0 is alpha 1 to the 0 plus and some plus alpha n to the 0, which is equal to n. And P1 is just alpha 1 plus alpha 2, which is equal to E1. And P2 we already did, that's alpha 1 squared and some, which we said was E1 squared minus 2E2. P3 is already getting a little bit messy to do. Fortunately, there's a neat way of doing this using Newton's identities, which I will now explain. So the idea of Newton's identities is you notice that x minus alpha 1 times x minus alpha 2 and so on is just x to the n minus e1 x to the n minus 1 plus e2 x to the n minus 2 and so on all the way down to plus or minus en. So the alpha i's are just the roots of the polynomial whose coefficients are the elementary symmetric functions. And what do you do if you've got a product? Well, you can always simplify products by taking logarithms, which is a good thing to do because it gets rid of the products and replace it with sums. Well, there's a disadvantage with taking logarithms in that you've introduced logarithms, which are this sort of rather complicated transcendental function, and this is an algebra course, so we really ought to be just working with algebraic things. So to get rid of the logarithms, so the logarithms turn products to sums, and to get rid of the logarithms we then take derivatives. So this changes log of x minus alpha to 1 over x minus alpha. So what we want to do is to take the logarithmic derivative of both sides. Well, d by dx of log of f is just the derivative of f divided by f for any function f. And you notice that this operation is purely algebraic, that we can define the derivative of any polynomial just by saying the derivative of x to the n plus a n minus 1 x to the n minus 1 and so on plus a 0. We can just define it to be n x to the n minus 1 plus a n minus 1 a n minus 1 x to the n minus 2 and so on. So this gives you a perfectly good definition of the derivative that works over any field whatsoever, even if it's characteristic p or whatever. And you can check that most of the usual properties of derivatives hold. For instance, we've got Leibniz's rule d by dx fg equals d by dx f times g plus f d by dx of g, and this still holds over any field. And you can either do that by doing a slightly tedious calculation, or you can just observe that this holds for complex polynomials. Therefore it holds for polynomials over a ring of polynomials over x in several variables, because you can embed this in the complex numbers, and it then holds for any ring because any finite number of elements in any ring is an image of this ring here. So all the algebraic rules for derivatives tend to work if you're working over any field. You don't need to worry about limits or anything like that. So what we're going to do is to take this identity, x minus alpha 1, x minus alpha 2, and so on, equals x to the n minus e1 x to the n minus 1, and so on. And let's call this thing f of x, so I don't have to keep writing it out. And we're going to apply the logarithmic derivative to both sides. Well, the logarithmic derivative converts products into sums, so this is the sum of the logarithmic derivatives of x minus ai. So we're going to get 1 over x minus alpha 1 plus 1 over x minus alpha 2 and so on. And here we're going to get f prime of x over f of x. And now we're just going to expand both sides as power series and see what we get. We're going to expand them as formal power series and not worry too much about convergence. So let's see what we get on this side. Well, we get 1 over x plus alpha 1 over x squared plus alpha 2 over x cubed and so on coming from this. So if we sum over all of these, we're going to get p0 over x plus p1 over x squared plus p2 over x cubed and so on. And this is very nice because these are the sums we're trying to work out. On the other hand, on this side, well, we get a quotient. Well, quotients are a bit of a pain to work out. So what we're going to do is we're going to take this copy of f of x and just move it over to the right-hand side. So we get this sum times f of x, which is x to the n minus e1 x to the n minus 1 and so on, is equal to, and now we've got the derivative of f, which is n x to the n minus 1 minus n minus 1 e1 x to the n minus 2 and so on. So now we've got a relation between the pi's that we were trying to find and the ei's that we wanted. And all we have to do is we equate coefficients of x to the power of something on both sides, and let's see what we get. Well, if we look at the coefficient of x to the n minus 1, nothing very exciting happens. We just get p0 equals n, which we knew about already. If we look at the coefficient of x to the n minus 2, we find p1 is equal to e1, which we already knew. The next one, we find p2 minus e1 p1 is equal to minus 2e2. And now this doesn't quite give us a formula for p2 in terms of the elementary symmetric functions because we've got p1 appearing there, but that doesn't really matter because we know p1 already. And similarly, we get p3 minus e1 p2 plus e2 p1 is equal to 3e3. And we go on like this, p4 minus e1 p3 plus e2 p2 minus e3 P1 is equal to minus 4E4, and so on. So this gives a very nice series of identities which allows you to work out the PIs explicitly by recursion in terms of the elementary symmetric functions. So let's just do an example. Let's take the polynomial z cubed plus c plus 1 equals 0, and we want to know what is the sum of the fifth powers of the roots. I have no idea why you would want to know this, but if you do want to know it for some reason, here's an easy way to work it out. Well, we're just going to let the roots be alpha 1, alpha 2, alpha 3, and we want to work out the sum of the fifth powers is just P5. And we just work them out using these relations here because we know E1 and E2, and we find P0 equals 3, P1 equals 0, P2 plus P0 equals 1, so this gives us P2, and then we find P3 plus P1 plus P0 equals 0, and P4 plus P2 plus P1 is equal to 0, and P5 plus P3 plus P2 equals 0. So you can work out P2, P3, P4 and P5 recursively like this, and unless I've made a mistake, we find P1 is 0, P2 is minus 2, P3 is minus 3, and P4 is minus 1, and P5 equals 5. And if I've made an error in my calculations, please just keep quiet about it. So another example of Newton's identities are the Adams operations, which are in K-theory. And I'm not going to explain exactly what K-theory is. Instead, I'm just going to work out the simplest non-trivial example. So suppose we've got a vector space V, and suppose it's acted on by a group G. So in other words, it's a representation of the group G. Well, we can take the tensor product of V with itself, and this is still acted on by G because G acts on both of its components. However, this tensor product splits as a sum of two vector spaces also acted on by G, which are called the symmetric square and the alternating square of V. And this one here is spanned by things of the form A tensor B plus B tensor A, and this is spanned by things of the form A tensor B minus B tensor A. So you can see that this thing here has dimension n plus 1 over 2 if the dimension of V is n, and this is dimension n minus 1 over 2. And the Adams operation on V, denoted by psi squared of V, is equal to s squared of V minus lambda squared of V. So we're taking two vector spaces and subtracting one from the other. Well, you may think this doesn't make any sense because you can't subtract vector spaces from each other, but you can. What we're going to do is just take the semi-ring of all vector spaces under direct sum and tensor product, and then just force it to be a ring by sort of just decreeing that we can subtract vector spaces. So this is just like the definition construction of the integers from the natural numbers. You just sort of forcibly decree that you're allowed to subtract things. So this isn't really a vector space, it's something called a virtual vector space. The question is, how does G act on this virtual vector space? Well, that doesn't make a lot of sense because G obviously can't act on this because it's not a vector space. However, we can still ask what is the trace of an element G in G on this space lambda squared of V. And this does make sense because the trace of an element on a vector space is additive, so you can still define the trace to be the trace of G on this minus the trace of G on that. And the trace of G, so the trace of G on s squared of V is just sum over I less than or equal to j of alpha I alpha j, where the alpha I are the eigen values of g on v. And the trace of g on lambda squared of v is sum of I less than j of alpha I alpha j. And you should notice there's a sort of subtle difference here, because here I've got I less than or equal to j, and here I've just got I less than j. So these aren't quite quite the same. So the trace of g on psi squared of v is, we have to subtract these, and we just get sum over all I of alpha I squared. And you notice this is just this element P2 that we calculated using Newton's identities. Now, what I've done here is just for the tensor product of two copies of the vector space. We can also take tensor products of n copies of the vector space and do a rather more complicated operation and extract from something called the Adams operation of degree n. And here the trace of an element g on the nth Adams operation just turns out to be Pn, the sum of the nth powers of the alphas. So in order to work out what the Adams operations are explicitly, you need to use Newton's identities for expressing these numbers Pn in terms of the elementary symmetric functions. Now I'll describe another thing you can calculate from elementary symmetric functions, which is the discriminant of a polynomial. And let's explain this. Suppose I look at the alternating group. Let's look at the alternating group A3 acting on three variables. Let's just make them act on x, y, and z. And so this is really just a cyclic group of order 3, and a generator is just taking x to y, y to z, and z to x. And I want to know, what are the invariant polynomials? Can we find polynomials on this that are invariant under A3? Well, there are some obvious examples. We can take the elementary symmetric functions e1, e2, and e3, which are x plus y plus z, xy plus yz plus cx, and xyz. So these are actually invariant under the whole symmetric group, which is bigger than A3. And we want to know if there are any other invariants. So what others can we get? Well, suppose we look at the element g, which is just switches x and y. And suppose f is invariant under A3, but not necessarily under the whole of S3. Then we can look at f plus gf over 2 and f minus gf over 2, and f will be the sum of these. And we notice that this is invariant under S3, whereas this is anti-invariant under S3. What that means is if we act on it by a transposition of S3, this actually changes sign. So there are sort of two sorts of invariants of A3. There are the ones that are invariant under S3, and they're the ones that are anti-invariant. So we want to know, can we find any examples of anti-invariants of S3? And there's one obvious example. We can just take polynomial delta, which is x minus y, y minus z, z minus x. And you can see this changes sign if we switch any two of x and y. And furthermore, delta divides any anti-invariant. That's because any anti-invariant must vanish whenever two of these are equal, so it must be divisible by x minus y and by y minus z and by z minus x. So the invariance of A3 is the same as invariance of S3 plus delta times invariance of S3. So the invariant ring is, let's work over the complex numbers, it's going to be generated by E1, E2, E3 and delta. However, it's not the polynomial ring in these because these are not algebraically independent. We have to quotient out by some ideal. And you notice that delta squared is invariant, so it must be equal to some polynomial in E1, E2 and E3. So the full ring of invariants of A3 is described like this. It's this polynomial ring in 4 variables quotiented out by some ideal. And the problem is, what is this polynomial? Well, it turns out to be a bit of a mess. Delta squared actually turns out to be 18 E1 E2 E3 minus 4 E1 cubed E3 plus E1 squared E2 squared minus 4 E2 cubed minus 27 E3 squared. And the problem is, how do we find this? Well, we could obviously find it by doing some horribly long calculation. What I mean is there a reasonably easy way to find this? We can ask the same question in more variables. So more generally, if we've got a polynomial, say x to the n minus e1 x to the n minus 1 plus and so on, and suppose its roots are the numbers alpha I, what we notice is that if we put delta is product of I less than j of alpha I minus alpha j, then delta squared, which is product over I less than j of alpha I minus alpha j squared, is a polynomial in E1 up to En. And the problem is to find this polynomial. There's one case that we already know. If the polynomial is quadratic, x to the n, x squared plus bx plus c, then you know the discriminant of this polynomial is b squared minus 4c. You remember the usual formula for the roots of this polynomial. It's minus b plus or minus the square root of b squared minus 4c over 2. You can see the discriminant turning up there. So we know how to find the discriminant in degree 2. In order to find it in higher degree, we can use something called the resultant of 2 polynomials. And I'm going to stop here and leave the discussion of the resultant to the next lecture.